Okay, so for today, we're going to continue our thermodynamics. Today, we're going to talk about kinetics of a gas. All right, so let's talk a little bit about what a gas actually is, just some basic chemistry review. So remember, a gas is made up of tiny particles that are spread out and they're moving very quickly. So there is space between them. That's what matters. That makes it different than something like a liquid. A liquid has particles that are moving around, so they're sliding around each other, but there's not really any space between them. Okay? So that's what makes a liquid different. The gases will have higher speeds than the liquid, and they'll have more room because there's space to move more. Okay? Now, because there's more space, we are going to assume for here that there is no interaction. Okay? There's no interaction between each particle. So each atom is totally on its own. There's no interaction with each other. Now this is what we would call an ideal gas. All right. I know you've heard that before because we heard it yesterday, but that's one of the definitions of an ideal gas. Is there's no interaction and there's no energy loss with the collisions. Okay, now in real life there is some interaction. It's very small, and you don't have to worry about it at this level, of course. It's a fun equation, I can promise you that. But we're just going to worry about an ideal gas, which is going to act like this. Now we talked about what temperature means. So temperature is going to refer to how fast they're moving, and that's what we are going to be talking about today. So let's go to our old friend, the ideal gas law. So remember, this guy is PV is equal to nRT. Awesome. Hopefully you remember all of that. Now, let's say that I wanted to tweak this law just a little bit. Okay? So the PV is going to stay the same. But over here, I don't want to use moles, right? Because this is in moles. I want to talk about on a particle by particle basis. All right. Now for just particles, I'm going to use a capital N for, number of particles, right? So this is a particle as opposed to this guy here, which is a mole or whatever number it happens to be. Now, how would I convert moles into particles? All right. So if I want to convert moles into particles, I'm going to have to take my number of particles and I'm going to have to divide it by a very famous number, Avogadro's number, right? So I'm going to multiply this. So these are the same thing, right? Because remember, your moles is going to equal the particles divided by the Avogadro's number, the 6.022 times 10 to the 23. This is another number that's on your formula sheet. It's with all the other constants. So this is what we're doing here. So I'm replacing moles, which is the lowercase n, with particles, which is uppercase n, divided by 6.022 times 10 to the 3. That's a constant. It's Avogadro's number. Okay, so this is what we're swapping here. So I'm switching these guys out. So what this is going to turn into, I'm going to just do some rearranging here, is n is equal n times r over na. And then the t is still going to be there as well, okay? Now, the reason why we're doing this is because r is a constant and na is a constant. Both of these are just constant numbers. So we're going to merge them into a different constant. So this is going to equal n times kb times t. All right. Now this is the constant that's going to show up in the near future here. So this is still equal to PV here. So kb has a name because it's important. It's called Boltzmann's constant. Boltzmann. Two N's there. All right. So Boltzmann's constant is equal to 1.38 times 10 to the negative 23. Now that's significant because it's just R divided by NA, okay? So it's going to be a really little number because NA is going to be a really big number. Now N here is just particles, right? So how many particles there are? Now it's going to be a big number typically. If we're talking about 1 mole of objects here, your number of particles is going to be 6.022 times 10 to the 23. It's going to cancel out the Na that's there. You're going to get R. It's going to be everything just like usual. All right? So that's all well and good. So this you might have seen on your formula sheet. This takes care of that. So what we're going to talk about now is we're going to start comparing it to the energy, the kinetic energy of the gases. So what we did is we noticed that if you have a particular volume and there's more pressure, there's more force on the particles. That means there's going to have a higher kinetic energy. And the rate that it changes is going to be 2/3 times N times K. Now, kinetic energy, this is your average kinetic energy, because all the gases are going to be slightly different from each other, but the average kinetic energy is going to equal this. The more pressure you have, the more kinetic energy, because it's higher force, higher change in momentum, equal mass, so higher velocities. All right, so we have this. Now, we're not going to deal with the PV side of this so much, but we know that PV is equal to nRT, so we're going to take nRT, and we're going to make that equal to 2/3 NK. So far, so good? Okay. So what we're going to do now is we're going to do a little bit of rearranging once again. We are going to solve for K. That's what we're going to be looking for. We want to figure out an equation for kinetic energy. So K is going to equal 3/2 RT, RT N over N. So far, so good? Are we okay with that? Now, that looks really complicated. Yes, I agree with you. However, we're going to do some simplifications here. Buckle your seatbelts. I'm looking at some of this stuff, and I'm seeing things that can cancel. All right? So, some things we know. N over N, well, little n over big N. We know what this guy can equal. All right? Where does it come from? It comes from this part up here. N is equal to N over NA, right? N is equal to, little n is equal to big N over NA. So that means, if we do a little rearranging here, so N over big N is equal to 1 over NA. So far, so good? So the little n over big N, this can be simplified a little bit, simplifying the whole thing here, to RT over NA. All right, that came from right here. Now what we're going to do is there's one more step. We know what R over NA is equal to. Okay, where's that? That's all the way over here. So we know that R over NA is equal to KB. So combine this all together. K is going to equal 3 over 2 KB times T. All right, let's try to tie this down to remember what all the things stand for, because I know it was a lot. K is your kinetic energy, and it's going to be in joules. 3/2, just a number. This is your Boltzmann constant. It's just a number. It's going to be 1.38 times 10 to the negative 23. This is in your formula sheet, that constant there. T is your temperature. Now remember, your temperature has to be in kelvins because you're doing an absolute. Yeah, I know what you're saying. There's a lot of K's around here. It's okay. It's all right. Hey, and this formula right here, this guy is going to be on your formula sheet. I promise. This one's on your formula sheet, the one we just talked about, and this guy is also on your formula sheet there. It's with the gas law, with the ideal gas law, the PV equals nRT. Okay. Now with all that out of the way, let's do a practice problem. Oh, sorry. We're not going to do a practice problem. We're going to talk about velocity. So what we just talked about here is K is equal to 3 over 2 KB times T. All right, that's just coming straight from the other side. Well, we do know something about K, and I know that you were thinking about it. I could hear it from here. K is equal to 1/2 mv squared equals 3 over 2 KB. Now, this formula is not on your formula sheet for your AP test, and that's okay, because you know what both sides are. You know your kinetic energy formula, and you know this one because we just talked about it. So now let's do a little simplifying here. So we can cancel out those 2's in the denominator. So mv squared is equal to 3 kBt. Solving for v, we're going to get v squared is equal to 3 kBt over m. I'm just going to leave it like that. Now, the important thing to realize for here is this is a v squared, so sometimes this is called the root mean square. Because if you solve for velocity, take the square root of the average kinetic energy squared. Okay? It is just, I'm sure you've heard this mentioned before. It's just a mathematical way of averaging. It's slightly different, but it works basically the same way. Now let's do a practice problem. So we know the root mean square of the speed of a gas is 256 at some temperature. The gas has a molar mass of 32 grams per mole. Right, molar mass, remember, means per mole. What would be the root mean square for a heavier gas of 131? All right, let's do it. So we're going to jump into that formula we were just talking about here. So we know that K is equal to 3 over 2 KB times time, but we also know that we've got a 1/2 mv squared is equal to 3/2 kBt. I know we just did this, but we're going over it again because we're trying to practice like we would on the AP test, where you won't necessarily remember this one directly. You might, or the velocity one directly, you might have to work up to it. So solving now, we're going to get v squared is equal to 3 kBt over m. 2's canceled out, m went down. All right. So the root mean square is 256. So we're going to plug this into here, 256. Now that's going to be squared because that is the velocity. We have to square it to get the value here. Equals 3 times the constant is always going to be the same, 1.38 times 10 to the minus 23 times t. I don't know what t is. I'm going to solve for t on this first one, and I'm going to figure out what the speed is on the second guy because they're at the same temperature. Now, for mass, what is the mass? Well, the mass is 32 grams per mole. So how much mass is a particle? Well, we know that it's got 32 grams per mole. Yeah. So that's going to be 0.032 kilograms per mole. Okay. Well, that's per mole, right? But how many kilograms is one particle? Well, we're going to divide by how many particles are in a mole, right? There's 6.022 times 10 to the 23 particles per mole. So each particle is going to have this, whatever this fraction is. I'm not actually going to type it in. I'm going to just leave it in the equation here. So each particle is going to be 0.032 divided by 6.022 times 10 to the 23 kilograms, whatever that fraction is. The reason why I'm leaving it like this is because you have a negative 10 to the 23, positive 10 to the 23. It makes it a little easier. You can just cross those out. Okay, so this guy, once you solve it, T is going to equal about 84. All right, now remember, this is in Kelvin, so this is pretty chill gas. But that's what we get for the temperature. All right, so let's look at part 2. Part 2, now we know the temperature, we're going to figure out what the speed of the second gas is. So I'm going to start from here. V squared is going to equal 3 times KB, 1.38 times 10 to the negative 23, times temperature, which is 84. We're going to divide by the mass. This mass is going to be 0.131 divided by 6.022 times 10 to the 23. All right, same kind of algebraic trick falls into place. So V is going to equal about 126.5 meters per second. Now let's think about it before we keep going. Does that answer make sense? Yes, it should make sense. This guy has more mass. There's more mass here, so it's got to have a lower speed because they have the same amount of kinetic energy. All gases, it doesn't matter what type of gas it is, have the same amount of kinetic energy at a particular temperature. All right? And how they relate to each other is using this formula. Okay? Now, you might see other people do it in a slightly different way. That's okay. There are other ways to do it. Some people don't use this KB. Some people use the R and the N and all that stuff. If you combine them together different ways, you might be able to get molar mass down here instead of just mass. Doesn't matter. There's lots of little, depending on how you combine the units together, there's lots of different ways to do it. But as long as you can figure it out, that's what really matters here. All right, let's look at the next one. So a cylinder container of radius 15 centimeters and height 30 centimeters contains 6 moles of gas at that. How much force is exerted on the liquid? So this one's a little different. This is more a review from yesterday. But if you think you can do it, go ahead and pause the video and see if you can. I'll catch up to you as soon as I finish drawing this wonderful picture here. Okay, so what we're going to look at is we are going to be doing a PV is equal to nRT. So pressure, we don't know what pressure is. We're going to figure it out because that's related to force. So we're going to do that in a second here. P times V. What's the volume? Well, we got to figure that out. Volume of a cylinder is going to be pi r squared times h. Pi times r, which is 0.15. Don't forget, because you got to do it in meters. 0.3. Put them together, and we're going to get 0.021 meters cubed. Nice. Times n, little n is 0.6, because that's in moles. Times r is always the same, 8.31. Times T, we know what the temperature is, 433. So solving, we get pressure is equal to, I'm going to take it up to kilopascals. We're going to get 101.8 kilopascals. Nice. Now, is that how much force is exerted on the lid? Well, we can figure out what the area of the lid is, which is fine, but there's something else at play first. If you have a gas that's inside of this container, it's going to be pressing up, okay? But there's something else that's pressing down, and that is the weight of the atmosphere. The atmosphere is going to be pressing down as well. So what we're going to do is we're going to subtract the weight of the atmosphere. Do you remember what it is? It's 101.3 kilopascals. All right. So we're going to subtract this. We're going to get half a kilopascal or 500 pascals. Now to figure out how much force, how much net force there is on this thing, what we're going to do is we're going to use the definition of pressure. Remember, pressure is equal to force over area. We know what pressure it is. It's going to be 500 pascals. That's going to equal some newtons divided by area. Well, what's the area? Well, the area is going to be your pi r squared, with your radius was 0.15 centimeters. All right, so we're going to plug that in, solve for F. The force that you need to keep this shut, to keep the lid from flying off, is going to be 36 newtons. All right, now that makes sense. That's what, about 3.5 kilograms, 7 pounds. Sounds reasonable. 8 pounds maybe. Either way, that's how much force it takes to hold it together. All right, hopefully you had fun. Smash that like button and subscribe. We'll see you tomorrow.